right. Hello, everyone. My name is Omwesi Jesses. I'm from Group 19, and we are dealing with age-optimized acoustic phenotyping for early detection of avian respiratory diseases. So basically, we had gone through data analysis and model training of some other different models. So this is the best model we happen to choose, and I'm going to take you through its architecture. So what we do, we convert the one-dimensional audio we receive from the chicken to two dimensions, whereby we have, like you see, there's pre-processing of that image, one-dimensional image. It goes through the delta and the delta squared. Basically, for delta, we are always dealing up with the velocity of that spectral features. Then the delta squared, where there is a star, we talk about the acceleration of those spectral features. So after that, uh, those features go through the vision transformer, or what we call the VIT architecture. It's an already built version of that model that handles acoustic sounds. So they are converted into different patch embedding. This is whereby we always have small pieces of those spectral features. We convert them into small patches. So for each patch that goes through those transformer layers, it is always assigned a CRR token. So a token, for each token, it belongs to a patch for that before, as it goes through the vision transformer. So from there, we are able to classify uh, the output, whether the chicken is sick or healthy, uh, while the model is ignoring environmental factors like noise uh, that, that are mostly affecting the model performance. So these are the results we got from the model that we decided to deploy that outperformed other models. So one, we talk about the precision. Precision here, we are always talking about the quality of the prediction. For example, if you predicted maybe a certain number of chicken is healthy, is it actually that number that is healthy? Or so here we are always talking about uh, the quality. Then for recall, we are always talking about the quantity, the number. So if you talk about a given number is unhealthy, how big is that number? So based on our results, from the results that are demonstrated here, 90%, 92, you can clearly see that the model is generally performing well. Then for the F1 score, we are always trying to find a balance of between the precision and recall. We make sure that the model doesn't only focus on the quality of the prediction, but also the quantity. Are we able to find out that the number of the healthy birds is equivalent to the number of the unhealthy? Then for the confusion matrix, we are trying to make sure that the model doesn't uh, finds a balance between the different predictions. So from here, as you can see, we have the healthy. So for example, like the 44, it's the intersection of the healthy and the actual unhealthy. So we are trying to find the balance in between two different predictions. So we actually have the 44. So the actual unhealthy and the healthy the balance was found at 44. Uh, Basically, those are some of the results.
Hello everyone, my name is Ainemba Wasprita and I'm going to talk about basically the demo of our our product. What is in the image is it is just its interface, and from here you can see that you can upload an audio or you can record. So after recording that audio or uploading it, you first let it to process, then after it is pre-processed or uploaded, then you can tap on this button that is for analyzing, and then you let it analyze. Then after it analyzing that audio, the results appear here. You can see it is the confidence score. It either tells you that that audio is for a healthy chicken, or it's just noise, or it is unhealthy chicken. And then in case it is unhealthy, it gives you a recommendation that you can go and visit a veterinary doctor. It just appears here. Then next, I'm going to talk about the deployment architecture of our model. These are basically the steps that we followed while deploying our model. First of all, it, we followed a two-phase approach, and the first one is the training phase. The training phase that learns from the poultry audio, and then the next one is the deployment phase that makes the model available for service. Then for the model, we used a vision transformer. For vision transformer, it is basically for images, but then we adapted it by converting our audios into spectrograms, which allows the vision transformer to learn the sound patterns effectively. Then for input, our inputs is just the audio, which is dot wave, and uh, the audio, it is converted into 3-channel spectrograms so that it can look like an image for easy processing. And then the pipeline, it generally works in 4 steps. That is, it starts with the audio that is being processed into features, and then a second, the features which are passed into a vision transformer, and then the third is the model. The third is the model. The model applies a softmax function that computes the probabilities that help in the prediction. And then after prediction, of course, the results will either be healthy or unhealthy, and then noise. And then also with API endnotes, our project, we made it exposed to those API endnotes such that the users are able to send audio and receive predictions their comfortable places. And then for the deployment, we basically used Python and PyTorch for just development, and then to make our application and the model online, that is why we use the Hugging Face spaces. And finally, we were successful with the deployment, and that is the link to our deployed model.
Hello, my name is Collins Isuga, and I'm taking you through the operational flow or how we use our product. So we have about 5 departments. We have the user, the web app, the API, the model, and the output. So when you open the product via the web interface, start with the user uh, who uploads the audio that wants to be predicted whether it's from a healthy chicken or unhealthy chicken. We upload it into our web app by clicking the upload button. Then we select which audio we want, and mainly we take the .wav format audios. Then that audio, when you click analyze, the audio will be picked by the post method via the API, and it will be picked from the web via the post method. Then I'm going to pick the model via the API, of which the model was trained on the different categories of the audio clips. So when it picks that audio, the model is going to act on it. Then when it acts on it, we have the transformer that is going to work on that audio clip in our trained model. Uh, then it will do the feature extraction. After doing the feature extraction, it will further go through the classification of the three categories of the sounds we have. Then after classification, we are going to pick the output of whether it's healthy or unhealthy. Then after that, we are going to pick the prediction via the API, and will appear as the prediction or the actual output via the web interface, and this one will demonstrate to us whether the output is healthy or unhealthy. And when we find out that maybe it's unhealthy, we are going to receive a warning telling us to immediately visit the veterinary doctor. Then when you go to the limitations, as we are using our product, first we had the computational complexity of the model, where at times, uh, at first the model was overfitting, so it couldn't distinguish between noise and unhealthy chicken, and we tried to overcome that limitation. Then the next limitation, it was acoustic background noise interference. For example, maybe the sound from the fans or the feeding troughs, it was also a hindrance as we are training our model. Then data imbalance and anomalies. Like for example, at first we had a few data samples of the noise sample, and we couldn't get the actual or the right prediction or the accuracy balance of the training. Then the next steps talk about diverse data sets, using different data sets, or using the real-time recording from the chicken houses. Then you have edge optimization, where we are going to use maybe real-time data collection and like collecting the data, or using an app from maybe a phone or another gadget. Then we want to use real-time monitoring and prediction, where we collect data directly from the chicken house, we analyze it and give the prediction instantly. Then the conclusion, you have high accuracy diagnosis, where we eliminated uh, then for the high accuracy diagnostics, it's the model is works effectively to distinguish between the different classes, whether it's healthy or unhealthy, according to the prediction of the uploaded audio clip. Then for effective feature engineering, this is more of creating more features from the already extracted features so that it can easily easily extract each and everything that is in that audio clip uh, for easy prediction. Then the ready edge architecture. This is where we can use maybe local hosted devices which can give us real-time analysis of the predictions. Then these are some of our references that we managed to get and use through our training and model architectures. Then acknowledgements, we have our supervisor, Dr. Mr. Galwango Marvin, Department of Computer Science, then also the Makerere University. Thank you for listening. This was our submission.